Welcome to the second episode of the LIBTalks series, brought to you by the Western New York Library Resources Council. Today our guest is Derek Reihe, Director of Research and Marketing for Talyor Metalworks, Inc., and he will be discussing robotics initiatives as a gateway to STEM and STEAM programming in libraries.
I'm Derek Reihe. I was invited to the library to give this presentation about using robotics as a gateway to STEM and STEAM. I do research and development at a large metalworking company locally, and I'm also relatively heavily involved in arena combat robotics. Large robot programs are awesome, but they are also extremely expensive and out of scope of what most schools, libraries, educational facilities can fund. They also have a large focus on a very small number of people, so you don't get a ton of benefit from dollar by dollar what you're actually trying to accomplish. So the key to bringing people into STEM STEAM is always going to be enthusiasm, and it's hard to get people really excited about math or about coding or about motion control, just because they're hard to get into. If you don't have that way of thinking that you can envision what's going to happen when you press go on this code, it's not going to be something you want to do. The math is very hard. Like, what is cosine? What is sine? If you can't visualize it, then you can't really do it. You might be able to do the math, but you can't. When are you going to use this? Is the common question. So enthusiasm is always going to be the key to unlocking someone's potential. I have two examples here on this slide. Two friends of mine, Ray Billings, who's the current champion of BattleBots. You've seen him on TV. He started out as a security guard. He now works for Intel, I believe as an engineer, but I'm not 100% sure there. Max Maxim is another one. It was a plumber, and now he has, I believe he runs a fabrication operation. Someone is going to send me an angry email because that's probably totally wrong. Anyways, the focus on math, programming, and without some sort of end goal is what makes people like these who could be in this field not be in this field. They just don't have, when they started, they don't have the enthusiasm, they don't have the drive to really get there, even though they have the potential to get there. For example, here is a robot that I built in high school in 2001. It looks fairly complicated, but that's only half the drivetrain. And then we add the lifting arm, and then we add the weapon. And this also almost burned down my house at least twice. Well, my parents' house, but it almost burned it down twice. Just because it was so complicated, and we didn't really know what I was doing. I was in high school. And probably you don't want to do this. It's a little bit dangerous. In 2016, as you can see, everything is simplified. Batteries are much more powerful. Controllers are integrated and don't require any sort of programming whatsoever. You pretty much just plug it in and you go. That's just how the technology has gone forward. With Arduino and Raspberry Pi and these other small platforms being pushed forward by the demand for smartphones, drones, relatively complicated toys basically, the cost has gone down. On the left you have the Boston Dynamics Mule, which is more expensive than any of our houses. I'm sure anyone reading this or watching this. It's, I want to say, $1 million, and it's really cool. And it's walks around, and they were supposed to put loads on it so it could carry things over uneven terrain. On the right is a 3D printed hexapod that probably costs $50, if that. So these sort of technologies pushing forward are what's going to bring younger people into this. You're not competing with a wheel and a stick anymore. You're competing with hundreds of millions of dollars of video games and all kinds of products that are built for immediate rewards. And working through this is how we're gonna get people interested in this. So Raspberry Pis, for example, are ridiculous for what they are. For what a computer was a couple years ago, like a quad-core 1.2 gigahertz computer, probably more powerful than the workstation you're on right now costs $40. And they're about that big, they're fully integrated, they have monitor outs, and you can program them to do whatever they want, whatever you want. As a programming interface, they have input-outputs, so you could open up a shell and just say, send a signal to this output and that LED will go on or that little motor will turn. And it's a much more immediate reward than a breadboard with little sticks or pressing the switch and maybe a little light goes on. It gets people more involved because they're working towards something, especially if you can put, for example, a 3D printed robotic arm with a couple servos might set you back $30. But when the person's typing in code, now they're taking that code and putting it into the physical world. They can see the exact results of what they're doing. Even if they're cutting and pasting code that's already been prepared, they can see what it's doing. Maybe they'll change a variable and the arm will move in a different place. Maybe you could have this just doing things and they could put a block there and the robotic arm will take it and take it over there and they can see the code actually executing and doing its thing. Motion control is where the future jobs in this field are going to be. Robotic creation of parts, manufacturing, those kind of jobs are where everything is going to go towards. There isn't going to be as many factory workers, especially in this country, and farm workers as vertical farming becomes a thing. It's not a way we can push forward the species because we just have a lot of people. We're going to need to lean on machines. So motion control is where we want to be, where we want to be teaching people to go to. 3D printing is it's a motion control field, but it's additive instead of subtractive machining. You're adding material. You're not starting with a block of material and removing parts of it. You're starting with nothing and slowly adding machines. People can 3D print houses now. They can 3D print just about anything, and because of that, complete freedom almost, it's hard to use because you go to someone and say, hey, we can make anything, and they say, great, what are we going to do with it? And that's a hard thing to really grasp, is you can make any physical object, go. And people just don't know what to do. You can use a 3D printer to build another 3D printer that's larger. You can use it to build tools. You can use it to build educational props. Like I said, cheap servo-powered 3D robotic arms and things might cost $2,000 a couple years ago. You have a $15 Arduino and a couple servos. And sending code to them is now all simplified and open source. There are websites like Thingiverse and Yegi and I'm sure other ones, those are the two that I use, that give you free 3D models, so you don't need a whole lot of CAD CAM experience in order to create these objects. In addition, things like Autodesk Fusion 360 is a free software to education and hobbyists and anyone that makes less than $100,000 a year with that software. And it is awesome. It is a $20,000 CAD package 5 years ago. And you can create anything with it, basically. You can create objects to 3D print. You can send code from it directly into a CNC machine to cut parts out, like a router or a plasma cutter or a laser cutter or a mill. It does everything. And that's functionality that might have cost you $100,000 when I was in high school, and now it's free. Just pushing everything forward, basically. Arduinos are another small board, just like a Raspberry Pi. It's much more simple. It has inputs and outputs, and people could put code into it and just output signals to those, to LEDs, to switches, and learn basic circuitry, learn basic programming incredibly quickly. There's a website, circuits.io, which is, again, an Autodesk product, which is completely free, and you can do all this in a virtual space at no cost besides a Google Chrome, which is on basically every computer that exists. So in 1998 or so, BattleBots and Robot Wars were on TV. I was in high school, I think, at that time, and I'm like, hey, I need to do this. So I had a paper route, I had a part-time job, I garbage picked a tremendous amount of miscellaneous parts in order to build this terrible idea, which was basically a rolling bomb because I did not know how to build battery packs. That thing, we flew to San Francisco, we fought it, it started on fire and failed, and it was the worst moment of my entire life, and I came back and decided to work in IT. fast forward to a couple years ago, my godson saw Robot Wars, I think it was, on TV, and my sister, being the wonderful sister that is, says, you know, Uncle Derek used to do that. And I had I had a phone call about every day about when we were going to build him a robot. So after about 6 months of that, we decided to go to a small robot fight in Pennsylvania and watched, and he got a little chunk of a broken robot, and it was the best day of his life. And I was talking to people, and it occurred to me that all of this is about 100 times cheaper than it was in 1999 or so. Controllers were no longer $500–600 each, and you needed 6 of them. They're now, I think, brushless controllers average around like $30. So I decided to get back into that, and that turned into, I built my own mill in my basement. I turned it into a CNC mill. I built my own 3D printer. It's basically taken over my entire life. I assure you, I would have never learned fluid dynamics if I was just an IT guy and I just didn't want to make my robot swing a hammer better. Which is why I got into this field. You know, it's exciting, and it brings that enthusiasm out of people. So since then, I've left IT, and I now do research and development for a large metalworking firm, mostly to do with robotics, but also with some additive and subtractive machining practices. The world economy is based as such that some places labor is cheaper than in other places. And in this country, at least, labor is relatively expensive, so we need to turn to robotics in order to create things. That comes with positives and negatives. There aren't as many factory positions and workers in that nature, but there are more motion control, robotics, engineers, CAD/CAM people. There's more into that field. The other advantage is that because most of those machines are made here or in the Western world, in Germany or Switzerland and places, we're able to get them a lot cheaper. If your dollar is not really worth much because your labor costs are very low, and that's just how it is, you export cheap goods, you can't really as readily afford a $5 million CNC mill. Whereas if we're here working CNC machinery, it typically gets billed around $100 to $200 an hour. That $5 million mill now seems relatively reasonable. So subtractive machining is where you start out with a big block of metal. Typically it's aluminum these days, but it can be steel, it can be titanium, it could be anything. And over several steps with different tools, you will remove more and more of that material and basically reveal the part inside of that material, whatever you want it to be. And that can be done with lathes, with mills, with screw machines, all kinds of different machinery built for specific tasks. It can also be done at the hobby level with CNC routers and even woodworking tools, files, all that sort of thing. So that's the direction that industry is going, is more extremely high quality, high strength parts for like aerospace, for cars, for larger machines, not necessarily little trinkets that you would, you'd have in like a small toy or something like that. Those would typically be ABS or something. But the mold that makes those has to be made, again, on a giant CNC machine in order to make those molds last. You could make those molds out of sand, but the outside would be lumpy and the parts wouldn't mate and it would just look bad and no one would buy your product. Additive manufacturing is when you start with nothing basically and you're laying down layer after layer of material. In the case of 3D printing, it's usually lines of plastic about the thickness of a human hair, and you lay thousands and thousands of these layers and you end up with an object. You can actually 3D print just about anything. You can 3D print wood or stone or bronze or copper, just about anything. Typically, they will take whatever material you want and grind it up and put it into water-soluble plastic, put the part into water when you're done, and you're left with the stone or the wood or whatever you wanted to make that part out of. And 3D printers have the advantage of the same thing as a lathe can do, is you can make the machine with the machine. This 3D printer is almost entirely 3D printed except for some of the larger parts which were just too big, which could be fabricated with hand tools if you wanted. The metal frame obviously was not 3D printed, but everything else was. The electronics ended up costing around $60, and another $60 to $80 in hardware maybe. And this printer has a build area of around a foot by a foot by a foot. So it's around 20 to 100 times bigger than most of the more expensive off-the-shelf options. So that's about my presentation, about where we're going with the technology of tomorrow. I'll send some more educational guides and some links and stuff to the people running this so they can distribute those along with this. We'll put them maybe in the link below. And you can get started if there's any questions. We're available here to answer them, and we'll do the best that we can. And thanks for your time.
Thank you for joining us for another installment of LIBTalks. Special thanks to the Buffalo and Erie County Public Library for the use of the Launchpad in creation of this presentation, and many thanks to these organizations for their assistance in the making of the LIBTalks series. Stay tuned for our next episode out in June.